Hello. We're going to talk about solving equilibrium problems, the equilibrium constant, and do a bunch of practice problems. So I'm going to tell you in a few places during this slideshow to pause your video and try it out, and then I'll have the answers for you after that. So we're going to derive what is called the equilibrium constant from what we already know. Given a general equation where the lowercase letters are the coefficients in front of the species in the reaction, we're going to use this definition from our last lesson that the forward rate of the reaction is equal to the reverse rate of the reaction when the reaction is at equilibrium. Thus, if we use the rate law equations for those two rates, you have that K rate constant from the forward and the K reverse rate constant there with your concentrations and your coefficients as the exponents. We can rearrange this to have just our K value, so the forward rate constant divided by the reverse rate constant, and then get this expression where you have the products over the reactants all to their own coefficients. Sub KEQ in for the other two rate constants, and that's what the equilibrium constant is. Note that this is for the rate determining steps or one-step reactions, since we are directly taking those coefficients to be the exponents. Some conditions here. It is a single-step reaction, as I just mentioned. The temperature will affect the rate of a reaction, thus the equilibrium constant is always defined at a constant temperature. So here's the first example. We're going to do two where you just write the equilibrium constant expression given two reactions. And we're going to be looking at, for I think this whole lesson, all gaseous reactions, and then next week we'll dive into some aqueous reactions. The concept is the same. I'm just going to kind of scaffold it step by step with these different types. So here are two reactions where I would like you to write the KEQ expression, and I'll take them up in a second. The second one will be if you have a pure solid or liquid, then you don't really have a concentration, right? You can't say you have a concentration of a solid, and if it's a pure liquid, then it's not aqueous. It's not ions dissolved in water. So they do not affect your equilibrium. You won't include these in your reaction. For these two reactions here, just get myself out of the way there, like water becoming a gas, or ammonium chloride decomposing into ammonia and hydrochloric gas, or hydrogen monochloride, you will not have the solid or the liquid as part of the equilibrium expression. So pause your video now. You can look back and try the two examples, two questions from example one and these two. So hopefully this is legible. In the first example, you have the dinitrogen tetraoxide as the product, so it is over the nitrogen dioxide, which was the reactant, and that's to the power of 2. And in the second problem here, you're going to have your KEQ equal to ammonia to the power of 2 divided by nitrogen times hydrogen to the power of 3. Notice we're using the square brackets. That means concentration. This will be the same as the rate law expressions as well. In your second reaction here, we have the KEQ going, and it will just be equal to the water gaseous, and the KEQ for part B being the hydrogen monochloride and ammonia gas. Both of them will be gaseous, and you won't include the solid. Okay, for the third example, we're going to look at a question where they give you quantitative values. It says calculate the value of KEQ for the following system. Note that we don't have any coefficients here. It's a 1-to-1 to 1-to-1 ratio, and you are given in this equation that at equilibrium, the concentrations of all four species are that value below. So write out your equilibrium expression and solve for KEQ. Pause your video now. Okay, so taking up the third example here, we have your equilibrium expression with your products over your reactants. And because the concentration of the carbon monoxide and water vapor in the question were the same, I wrote them on one line squared. You'll see this a few different times as we go through a couple practice problems. And then it's divided by the concentration of carbon dioxide and the concentration of hydrogen gas. Put that in your calculator, you get 4.885, I believe. Rounded to three significant figures is 4.88 times 10 to the negative 3, and the equilibrium expression constant. So the magnitude of KEQ, when the equilibrium constant is much greater than 1, then the products are favored. You're going to be forming the products. If the equilibrium constant is 1, then we're at equilibrium, and at the macroscopic level, there's no change in the concentration of the products or reactants that would be forming. And if it is much less than 1, then the reactants are favored and you have the reverse reaction occurring. Here's just a graphical example of these showing how the concentration of the reactants and products are related at each value. Note that the concentration of reactants and products at equilibrium here, it shows them being equal. This isn't exactly correct for all reactions. The concentrations aren't necessarily equal at equilibrium, they're just constant. So it stresses one point but kind of tricks you and says something wrong for the next point. So one way to solve equilibrium problems, and this is what we'll be looking at for the next 2 weeks actually, is using ICE charts. ICE stands for Initial, Change, and Equilibrium. A couple things to note about ICE charts is all values that you plug into this chart for each reactant or product should be as a concentration, so moles per liter. So you may have to do some calculations to get to concentration. And in change, you're going to use an X. You're going to use a variable to show that is increasing or decreasing. And that X variable will always have the same coefficient that the species at which it's under has. We're going to do 3 practice problems here, and that will help explain how to use some of these. The problems are all with gaseous reactions, as I've said. Note that you could use partial pressures in the same way that we're using concentrations here. Because Dalton's law of partial pressures, they're going to be additive, if you remember that from grade 11. But we're going to stick with concentrations. So in our first practice problem, there's a 4-liter container, 2.5 moles of carbon dioxide is decomposing into carbon monoxide and oxygen gas. At equilibrium, we're given the concentration of the carbon dioxide, and we're going to use the ICE chart to find the concentration of oxygen and the equilibrium constant. So pause your video now, try it out, and I'll walk you through how we would do this. So I have written out here our equilibrium concentration, our expression here. And I think that makes it look a little bit better. So we have ICE representing the initial, the change, and the equilibrium concentrations. So we initially started with 0.625 moles per liter of the carbon dioxide. Now I calculated that from the molar value and the volume that was given in the question. And we don't have any of our products. We're going to write X representing the change, and we're always going to use this coefficient. So if carbon dioxide is decomposing, then you're going to have minus 2X there, and plus 2X for carbon monoxide, and plus X for the oxygen gas. Those X's reflecting the coefficients here, meaning at equilibrium, the concentration of carbon dioxide will be 0.625 minus 2x. and the concentration of our reactants are just our X values. We can use our equilibrium expression to plug these values in. Note the carbon monoxide, which is 2X, would be squared in our equilibrium expression, and the oxygen is just X. And then our 0.625 minus 2X squared is our carbon dioxide. This value here that value here was given in the expression. We were told that the concentration at equilibrium was 0.125 moles. So our equilibrium concentration of CO2 was 0.125 moles. We can sub this value in and make it equal to 0.625 minus 2x, because we know that this is an expression for the concentration at equilibrium, which is a known value. Rearrange that to solve for x, and you get 0.625 minus 2x equals 0.125. That means x minus 125 divided by 2 is 0.25. To get our concentration of O2, that is just X. So that is the concentration of O2 at equilibrium. And then the last part of this question was calculating for KEQ, which you can do by subbing all of those values in, all of the X values as 0.25. And here you have 2 times 0.25 squared times 0.25 all over, and I'm going to write 0.125 because we know from the equation what that is. Plug all those values into your expression and you find the KEQ for this reaction is 4. So those are the two answers for practice problem number 1. Out of the interest of saving time, I'm going to do all 3 of these. So I know I just did the first practice problem, but I'm going to talk through it again in a little more detail in a second video, and go through practice problem 2 and 3 in detail in the second video. So let me just bring up the questions here and talk about them, and then you can attempt them and then watch the second video. I think that's better than pausing. So here, practice problem number 2. Given the KEQ for the following reaction is 3.5, and that 0.5 moles of nitrogen monoxide is found at equilibrium in a closed 2-liter container, calculate the original amount of NOCl gas that was introduced into the reaction vessel. Okay, here, so we're given actually the equilibrium and have to calculate the initial value. So you're going to see when I do this problem, I'm going to put in a new variable for the initial value of our reactant and calculate that value as we go through. Practice problem number 3 is 1.5 moles of ethene gas and 1.5 moles of bromine vapor will come to equilibrium in a closed 100 milliliter container. Find that equilibrium concentration of your product given that the KEQ for the reaction is 3.45. So here you are given both of the reactants' initial concentrations, and they want you to find that equilibrium concentration. You'll note here we actually have to use the quadratic formula. So if you get to a certain problem where you're trying to rearrange to solve for x, remember the quadratic formula is an option, and I'll take that up in the second video.